Hello everyone and welcome to the final talk of Takeover Week. We are the National Space Academy and we have taken over the National Space Centre's social media channels to talk to some really cool people all throughout this week. My name is Nat and I am here tonight with Elisabeth Matthews from the University of Geneva, who is an expert in exoplanets. Hi Elisabeth, how are you doing?
Hi, yeah, it's great to be here. Thanks for having me.
Thank you so much for your time. So I was wondering if you could just introduce yourself perhaps and tell us a little bit about what you do.
Yeah, sure. So I actually have some slides that I'll share. So my name is Elisabeth and I'm a postdoctoral researcher thinking about exoplanets. And specifically, I think about observations of exoplanets, so how we can find new exoplanets and kind of the interplay between the different techniques that we can use to find exoplanets. So I'm going to talk you through some of those techniques just quickly now. So the one that I'm the most specialist in, the one that's closest to my heart, is direct imaging, which is perhaps also conceptually the simplest way of finding exoplanets. So all we're doing is taking a picture where we can see the star and the planet separately, which sounds simple. It's pretty tricky, both because the star is between 1 million and 1 billion times brighter than the planet. So that's a really dramatic contrast that we have to deal with. And if you've ever taken a picture out of a window on a sunny day or near a light bulb, then you'll know that that bright source completely washes everything out and it's hard to see anything fainter in that image. And the separation between these objects is really close together as well. So because the stars that we're looking at are typically between 100 and 500 light years away, the separation between the planet and the star, as we see it from Earth, is so tiny that a single human hair held out at arm's length would cover both the star and the planet on the sky. So we need some really specialized instruments and also some really special data reduction algorithms to be able to detect the planets directly. And only about a dozen planets have been detected with this method. But I think it's really exciting because it has so much potential to tell us what the planets are like, as well as just where they are. Perhaps the most prolific technique to detect exoplanets is the transit method. So this is the method where the planet passes directly in front of the star. So this is now all within a single pixel. We're not seeing what's going on here, but if we monitor the brightness of the star really carefully, then when the planet goes right in front of it, the star will look a little bit fainter because some of that light will be blocked out. And then when the planet moves on in its orbit, the star will look back to its original brightness again. So we can see a really characteristic dip shape, and then we can infer that there must be a planet orbiting around that star. And we can also use dynamical methods, so we can look at the orbits. Now, we normally think about the planet orbiting around the star, but really both the star and the planet are orbiting around the mutual center of mass. So the planet is sweeping out pretty big orbits because it's quite small, so it's quite far from the center of the mass. The star is making much smaller orbits, but if we can detect those orbits of the star, we can infer the presence of a planet whose gravity is pulling the star around. So we can do that in the plane of the sky. That's a technique called astrometry, which hasn't yet found any planets, but there's a mission right now called the Gaia mission, which is predicted to find 10,000 planets with this astrometry measurement technique. So seeing the stars wobble in the plane of the sky. And we can also do a similar thing, thinking instead of the plane of the sky, of the direction into the sky. So we can see stars, they'll look like they're moving towards us and away from us as a planet orbits around them. That's the radial velocity technique, which was the first technique that was used to find a planet. So in that case, what you can see is that the Doppler shifting of the light. So that's an effect that you might be familiar with because if you've ever seen an ambulance go past you in the street, for example, as the ambulance comes towards you, the pitch is slightly higher because the sound waves are being squished together. And then as it moves away from you, the sound waves are being stretched out and the pitch is a little bit lower. So we can do the same thing with the light of the star. We can see as the star is coming towards us, the light is being squished together and it looks a bit bluer. And as it's going away again, the light is being stretched out and it looks a bit redder. And if we see several of those wobbles, we can infer there must be a planet there causing the star to wobble. So I've worked a little bit within all of these techniques, although as I said, direct imaging is kind of the technique closest to my heart. And I'm just going to show you a couple of my own direct images now. So this is an image, what you're seeing here, the star is actually in the very center, it's kind of blocked out. We use a coronagraph, which is a type of mask that's physically blocking the light in the very center of the image to try and block out as much of the starlight as we can. And then we try and do various data processing to try and get rid of as much of the starlight as possible. But this ring that you can see here just around that coronagraph, this is residual starlight, and then the dark patches are places where we've actually subtracted off slightly too much starlight. So that's all noise associated with the star. And then what you're seeing over here is a companion. Now, in this case, when I first saw this data, I thought it might be a planet. I got really excited. It turns out, actually, after a lot of careful work, we confirmed that this is actually a low mass star rather than being a planet. So this is a binary star system rather than a star with a planet orbiting around it. But this is a little bit what a planet detection might look like. We'd have a similar effect of a star behind a coronagraph and then a faint source near the star that we're able to image. I also detected a debris disk. So this is the HD 129590 debris disk. It's a really catchy name. So this is a ring of asteroids and then also lots of dust. So as the asteroids crash together, they generate all of this small dust. And the individual dust grains are pretty small and pretty faint, but in aggregate, they make this really bright signal. So again, you have the star in the very center behind the coronagraphic mask. You have all of this noise, and then you have this long signal, which is the edge, the front edge of this debris disk, which is oriented roughly towards us. So we can really see that front edge quite clearly, and then we can just very faintly make out some of the back edge of that disk as well. I'll just very quickly touch on how I got to where I am as well. So I took a pretty traditional route into academia. I went through school and then went to university and did a 4-year combined bachelor's and master's degree. I actually did that in natural sciences because I wasn't yet sure which science was my favorite. So in the first year, I did quite a broad portfolio of different sciences, and then I specialized into physics and then took many astrophysics courses towards the end of that as well. I then went on to do a PhD in astrophysics. So that's another 4 years of studying. And I think it's worth saying at that point, you're studying and you're a student, but you are also being funded to do that work. So you're on a government stipend typically for PhDs in STEM. So you're no longer racking up student debt and you're able to support yourself. And then since I finished my PhD, I've been a postdoctoral researcher. So that's kind of somewhere between a PhD student and then a lecturer. So you're working in a university environment, you've finished your training, so you're doing quite a lot of independent research, but you're not yet supervising your own PhD students or lecturing undergraduates. So most of the time I'm kind of sitting at my desk, working with data, writing code to process the data, and then also thinking about and writing about our results. But it's also one of the real perks of this career is that we get to travel a lot. So I sometimes get to travel to international conferences and talk about my work and meet with other experts in this field. And I was also lucky enough to be able to go to the Magellan telescopes in Chile. So you can see those on this image here. These are 2 6.5-meter telescopes in these 2 domes. And I was able to go and operate one of those telescopes for my own research as well. So I spent 2 years as a postdoc in the USA, and now I've been in Switzerland at the University of Geneva for about 6 months so far. And I'm expecting to be here for a couple more years and then potentially moving on to a lectureship or something else at that point. So I think that's a quick introduction to me, and maybe now we can move on to the Q&A session.
That's great. Thank you so much for that introduction there to what you do. So we've had a question come into the chat. Hopefully that has now been answered for you, Danny. But thank you very much for your question. And just a reminder that if you do have any questions, you can post them in our chat. So it's so exciting what you do. You're literally looking for planets outside of our solar system. So you mentioned the fact that you work in imaging. So are you looking for new planets, or are you looking to find out more about planets that have already been discovered?
Yeah, I'm primarily trying to find new planets rather than studying planets that have already been discovered. So because imaging planets is so difficult because there's so few planets known at all, I'd be really interested in characterizing the planets as well, but we kind of need to find more planets before we can then study what they're like. All the ones we know have already been quite comprehensively studied Yeah.
So how do you actually go about imaging an exoplanet?
Yeah, so we use big telescopes. I showed you on the final slide, the 6.5 meter Magellan telescope, and you need mirrors that are that big to be able to get the resolution that we need to separate the star and the planet. So that's the first thing, is you build a really big telescope, or you find someone else who's built one and is willing to let you use it. We then have a really special instrument. We use adaptive optics, which is a technique that deals with the atmosphere, essentially. So the atmosphere blurs out your instruments, and we have a real-time correction on the detector that's undoing the blurring of the atmosphere. We can then, because the light is quite condensed, so the signal from the star is a real, like, solid point source, we can use a mask which blocks out the star to try and reduce the brightness of the star, and let us get down to the faintnesses that we need for the planet. And then the final step is that we actually take lots and lots of images, and we move the telescope between each of the images. And the reason we do that is that the noise pattern is tied to the mirror. So if you move the mirror, the noise pattern moves, whereas obviously the sky doesn't change just because you've turned your mirror and your camera. So then we can use computer algorithms to analyze this whole stack of maybe 100 or 200 images and look at all the patterns that are rotating between those images and all of the patterns that are stationary between those images. And you subtract off the things that are rotating and you're left with the things that are stationary, and that should be the sky. And if there's point sources in that image still, then they might be a planet, or they might, as I talked about, be a brown dwarf or a star as well. But that's in a nutshell how we do it. Yeah.
Well, that's great. Thank you so much for that explanation. So how common are exoplanets and exoplanet systems?
Yeah, this is very much a current question, and to some extent it depends which planets you're thinking about as well. So we're not sensitive to all the planets. We couldn't detect all of the planets in our own solar system if we were looking at our own solar system from 50 light years away, say. So we only really have a minimum number on that, but we think there are more planets than stars in the galaxy. So planets are really common. The typical star probably does have a planet or more than one planet. But we don't know yet, for example, how common Earth-like planets are, because we just don't have the sensitivity to find them around very many stars. So we know planets are quite common, but we don't know exactly how common, because we need more data to answer that question.
And so from imaging, are there things that you can find out using that technique that you can't necessarily find out from some of the other techniques?
Yeah, so I think all the techniques are very complementary. So imaging in particular, I think some of the benefits of that are because we're directly collecting the light from the planet, we can perform spectroscopy. So that means that we're splitting the light into different wavelengths and comparing how bright it is at each different wavelength. And some of the highest resolution spectroscopy, so the most data points for a single planet that you can get, is typically for direct imaging because of the way that the light is separated from the star. You can also do spectroscopy on the transiting planets, but it's quite different because you're looking, in that case, you're looking at the starlight coming through the planet atmosphere, whereas for direct imaging, we're looking at the planet light itself. And another thing that we can do is that we can monitor the brightness of the planets as a function of time. So we can look at if they're variable, which could indicate that there's clouds in the atmosphere. So there's patches of atmosphere that are brighter than other patches. And we can also use that to determine how quickly they're spinning. So if we see a characteristic pattern and then it comes back again, then we know, for example, that the planet took 8 hours to do one full rotation, and we can use that to learn about the physics of these planets as well.
That's so cool. There's so much that you can tell just like from so far away. So when you're talking about nearby stars, what do you actually mean by nearby? How far away is that?
Yeah, again, it depends on which technique you're thinking about. For imaging, we're really only interested in things that are closer than 500 light years or so. And that's just because the further away you get, the closer together the planet and the star are on the sky. So the closer you are, the easier it is to do. For imaging in particular, we're really interested in young stars as well, because it's easier to find young planets with direct imaging. So most of the young stars, it turns out, are at around 400 to 450 light years. So that's kind of the sweet spot where they're close enough that we can still see them, but they're also young enough that we have a good chance of detecting the young planets in those systems as well.
So we've had a question come in from Sean, and Sean wants to know, many planets that have been found are hot gas giants. So do you think this is because they are more common, or do you think it's selection bias? Are they easier to find?
Yeah, it's a bit of both. You might have heard them referred to as hot Jupiters as well. So these are planets that are typically the size of Jupiter or even bigger, but they're also really close to their stars. They're closer to their star than Mercury is to the sun. So they're really hot and the gas is really puffed up. We hear about them a lot because they are the easiest planets to detect and they're the first ones that were found. So for both the radial velocity and the transit method, you just get a better signal if the planet is closer to the star. You can see it move around the star more often and it's bigger, so it's blocking out more of the star's light, or for the radial velocity method, it's making bigger wobbles. We think that around 1% of stars have a hot Jupiter. So that's actually not a particularly high occurrence rate. The smaller planets are more common and easier to make in terms of planet formation theory, but they're also much harder to find because they're so much smaller, so they have a much smaller signature in the data. Yeah.
Great, thank you. So Kieran has asked, do you have a favourite exoplanet or a favourite type?
So my favourite exoplanet is called Beta Pictoris b. It's such a cool system. It really has it all. So it's one of the first planets that was directly imaged. It's also in a system that has a debris disk. So that's another thing that I like to think about, and I think about the interactions between disks and planets. The planet has been directly imaged, but it's also more recently been detected with radial velocities and astrometry. So that means we can measure its mass as well. And it's also really close to edge on. So there was a hope that in 2019 it might pass directly in front of the star and we'd see it transit as well. And that didn't quite happen, but the planet was close enough to the star that some people were working on studying whether it might have moons or a belt of dust around the planet itself. And I don't actually know exactly the results of that work, but there's real interest in that system from that point of view. So it's a system that has it all, I think. Yeah.
So I guess this is probably a question that you are faced with all of the time in your area, but is the ultimate aim to find life on another planet?
That's definitely one of the big aims, probably the most common goal of people thinking about exoplanets is to find life. It's certainly not the only goal. So we're also interested in, for example, understanding how the solar system formed and whether the solar system is common or whether it's pretty unusual as a exoplanet system. But that question also relates to life, because then there's a question of, is there something unique about our solar system that allowed us to make life, allowed life to develop within the solar system. So definitely the most common goal of scientists is life, but it's definitely not the only goal within exoplanets. There's lots of other interesting things to do as well. Yeah.
So speaking of Earth-like planets, we've had a question from one of our space engineers. So Alex would like to know what you think the chances are of finding an Earth-like planet in the next 10 to 20 years.
We're getting closer and closer all the time. So often in the media, you'll see publications saying the most Earth-like planet yet. And you always have to be a bit careful with those because we're kind of inching closer and closer and closer. So at the moment, the easiest way to find those small planets is with the transit method, but the transit method is much more sensitive to planets that are very close to their stars. Now, if you look at really small stars, that helps with the transit method because the planet is blocking out more of the light. And also for those small stars, because they're much cooler than the sun, even if the planet is much closer to the star, it might be the same temperature as the Earth. So there are a few planets that are known that are relatively Earth-like in the sense that they're about the same size as Earth and also about the same temperature, but they're around these very different stars and we don't really know what that impact would have on the planet. So for example, the stellar flares are going to be a much bigger deal. The activity of that star is going to, even on Earth, we sometimes worry about solar storms and they can blow out like electricity lines and stuff. And that's going to be much, much more dramatic if you're that much closer to your star. A real Earth twin, I think if they're common, we will find an Earth twin within the next 10 years. If they're rare, we probably won't. And we can't really know how common they are until we start finding them. Although I would guess that they are common, given that rocky planets in general seem to be pretty common. Yeah.
And that leads quite nicely into Ben's question. So Ben would like to know what steps would be taken if an Earth-like planet were to be found, and how possible would exploration be, do you think?
Yeah, so if we find an Earth-like planet, the next step is to try and study its atmosphere and see if we can learn about the environment of that planet. Now that's a lot harder. So at the moment, the atmosphere studies using the spectroscopy technique that I mentioned earlier, we can really only do that on giant planets because our instruments just aren't good enough to do that for small planets. With the James Webb Space Telescope, which is scheduled to launch later this year, we'll be able to start to push to studying super Earths, so planets that are a bit bigger than the Earth, but definitely approaching being a little bit more similar to the Earth than to something like Jupiter. But really, to study a genuine Earth-like planet, you probably have to wait 20-ish years until the next generation of telescopes. And there's telescopes both in the US and in the European system that are being discussed and planned that would have the potential to perform spectroscopy on the atmosphere of these planets. So to really study the atmosphere of the exoplanets, look at what different molecules are there. And that's when you can start to think about searching for chemical imbalances. So for molecules that we think shouldn't be there, which might then imply life. But even that is 2045, I reckon, is the first date that you're going to have a real comprehensive understanding of the atmosphere of an Earth-like planet. So we've got a way to go still before we get there.
Cool. I'm going to get back in touch with you in 2045 then and check in and see how it's
back and let you know how it's.
Yeah. So we've talked a little bit about what you do and the science behind it. But what does your job entail? What do you do day to day?
Yeah, so most of the time I'm sitting at a computer. If I'm lucky, I get maybe 2 nights of observing time per semester. And some of that is physically going to the telescope and doing the observing. And some of that is observing remotely. So setting up observings. Essentially, you write a really long, really careful list of instructions, and then the support astronomer does it for you, which means you don't have to travel to Chile, which is both a good and a bad thing because it's quite time consuming to do all that traveling, but also it's really nice to be able to go and visit the telescopes in person. The rest of the time is then a lot of time working with the data. So processing it, looking at it, both visually checking that it looks fine, and then also running various computer codes to pull things out of that data. I'm then also writing up some of our results. So writing papers for publications and then dealing with the process of going from a paper draft to getting all your co-authors to sign off on it, to then getting the journal to agree that it's good enough to be published. And then also collaborating, so working with other scientists on their projects, persuading other scientists to help me with my projects, going to seminars to learn about other people's work, and going to conferences to talk with other experts as well. So it's quite a varied job, but most of it is desk-based rather than telescope-based.
So did you know this was always what you wanted to do?
I knew I liked science as a kid. I was the kid that was always asking why and like bothering their parents and being like, but how does this work? And I was good at it as well at school. I found maths and physics came to me quite naturally. So I knew I wanted to do science. It took me quite a long time to work out which bit of science. So I actually did a natural sciences degree, which meant that in my first year I did some chemistry and some material sciences as well as the physics, and then kind of specialized in. By the end of the first year of my degree, I knew that physics was the right bit of science for me. And then at the end of my second year, I did a placement over the summer doing some astronomy research, and I really liked that and was like, okay, I'm sold, I'm going to do the PhD. And then since then, it's just been kind of taking it as it comes, and there keep being good opportunities, so I keep taking them, but we'll see whether that continues, how that carries on in the future. Yeah.
So if there was a young person who knew that they wanted to go into astrophysics, or they knew that they wanted to go and do a PhD, what should they be doing?
Yeah, so the first thing is to try and learn as much as you can about these topics. So engage with the media, watch TV programs, or read popular science books, any way that you can delve further into this subject. It gives you something, I mean, if you're excited about the subject, then you'll enjoy doing that. And it also gives you something to talk about when you're potentially in interviews or meeting with admissions tutors or anything like that. And then I'd also say, take a look at whether your local university, for example, runs any shadowing schemes or summer projects or anything like that. And especially as an undergrad, it's a little bit harder at school, although there are universities that have opportunities for school kids, but certainly as an undergrad, take a look at whether you can spend a summer in a research lab somewhere, actually kind of getting your hands dirty, having a go at really doing this stuff yourself. And that's the best way to really be sure that you're actually going to enjoy the 4 years of research that you have to do for the PhD. And then the other thing to say is, don't be afraid of asking people for things. Don't be afraid of emailing a professor at your local university or going to chat to your tutor or someone and saying, hey, are there any opportunities? And sometimes they'll say no, and sometimes you won't hear back because they're too busy, but occasionally they'll say yes. And I'm still relatively early career, but it's already striking how often I've kind of got lucky, been in the right place, asked the right person for help, and there happens to have been an opportunity and they've said yes, and then I've got to do a summer of research, and that's kind of helped to get me here, I guess. Yeah.
Oh, that's great. Thank you so much. So there has been 2 questions I've asked everyone I've spoken to this week. The first of which is, given the chance, would you go into space?
This one's such a hard one for me because I would love to be in space, and you see the pictures the astronauts share, and I'm like, oh, it would be so amazing to be in the International Space Station looking down at the Earth. But I really hate roller coasters, and I think a rocket being launched off the Earth is probably a lot more stressful than a roller coaster. So I don't know if I could deal with the journey up there or not. Maybe I can just get like teleported up to the ISS. That would be ideal.
So you're going to wait till teleportation's been invented, and then good answer there. I like it. And the last thing, just to end on, is so I've asked you what you'd give, a piece of advice you'd give if you knew someone wanted to go to uni and do a PhD. But what about someone who wants to go into the space sector in general? Is there any general advice that you could end on?
Yeah, I think to some extent similar advice applies. Whatever you think you're excited about, just try and learn as much about it as you can, through talks like this, through TV, through books, anything. Maths and physics are important for a lot of space sector roles. So if you can do well at those subjects, then definitely those are good focuses, but they're not the only ways in. So there's roles within the space sector that don't rely on maths and physics as well. So if you really don't want to be doing maths, then look into, there's space lawyers, and there's people doing media within the space industry, and there's all sorts of different specialities. Space is a really diverse sector. So kind of trying to look at what your skills are and what different jobs there are in the space sector, and then where there might be a good match, what thing might fit for you the best is probably the way to go. And then again, looking for opportunities and applying for things. And I would also say, never be afraid of applying for something. Even if you're not sure if you have the skills, it's better to apply and be told no than not even put yourself forward. And occasionally someone will say yes, and then you might get a really cool opportunity out of it as well.
I think that's such a fantastic message to end on there. Just go for things, and you never know what's going to happen. So thank you so much for your time this evening, Elisabeth. It's really, really appreciated.
Thank you very much for having me. Yeah.
And thank you very much for watching. Just a reminder that you can catch up on everything we've been doing this week on the National Space Centre YouTube channel. If you want to get in touch with us, you can get in touch on Twitter at UK Space Academy, or you can visit our website nationalspaceacademy.org. Thank you very much for watching.